Hey guys, Elmer the Exponential Elephant here, and today we're going to be exploring exponential functions. But here's a question. What's the biggest kind of ant in the world? An elephant!
Okay, the first vocabulary term is an exponential function. That's a function of the form y equals a times b to the x minus h plus k, where a is not equal to 0, b is greater than 0 and not equal to 1, and x, h, and k are all real numbers. So here you can see some examples of exponential functions. This blue one right here is fx equals 2 to the x power, where a is equal to 1, b is equal to 2, x is there, and then h is equal to 0, and k is equal to 0. Same thing down here, except our a value is negative 1. You can see how that affects the graph of our exponential function. We'll get into that more later on. Second vocabulary term is exponential growth. That's the growth whose rate becomes ever more rapid in proportion to the growing total number or size. This occurs when y equals a times b to the x minus h plus k has an a value greater than 0 and a b value greater than 1. So here you can see our orange graph represents exponential growth, where it increases ever more rapidly in proportion to the growing size, or the x value, right? The y value increases rapidly as the x values increase. And you can see it's because our b value is greater than 1. Now, what if our b value is between 0 and 1? That's exponential decay. So exponential decay is a decline whose rate becomes ever more rapid in proportion to the growing total number or size. This occurs when you have our given exponential function, which has an a value greater than 0 and a b value that's between 0 and 1. So it's like a fraction, like a third or a half or a fourth, something like that. So if you have a b value being raised to the x power that is between 0 and 1, you're going to end up with something like this green graph right here, which is exponential decay. So as your x values increase, you decrease exponentially on your y values.
How do elephants call each other? On an elephone! Example time.
Now, example 1 says determine whether each table represents an exponential function. Explain why or why not. So we're given a table here, and we need to determine, does it represent an exponential function? So you need to check your x values and your y values. Two things. First, is there a common difference between consecutive x values? So here, you can see, yeah, we're going from 1 to 2, you're just adding 1. And then from 2 to 3, you're adding 1. And from 3 to 4, you're adding 1. So there's a common difference between two consecutive x values. Perfect. That's what we need to know. Next, is there a common ratio between y values? So here, between consecutive y values, we need to see, is the ratio the same? So 8 and 2. Ratio means divide, right? So we do 8 divided by 2. What does that give you? That gives you 4. Now, what about 32 divided by 8? What does that give you? Well, that's 4. Okay, cool. What about 128 divided by 32? What does that give you? That's 4. Excellent. That's exactly what we want to see. So, because there's a constant difference between x values and a constant ratio between y values, the table represents an exponential function. Okay, so that's all you need to see in order to determine, is a table representing an exponential function. Here, let's try that again. So is there a common difference between the x values? So here, from negative 1 to 0, that's 1. From 0 to 1, that's 1. From 1 to 2, that's also 1. Perfect. Common difference between our x values. Now, is there a common ratio between our y values? So what is 4 divided by 2? That's 2. What's 6 divided by 4? Well, that's 1.5. So technically, you could stop right here, but you could keep going. 8 divided by 6 gives you 1.3 repeating. So yes, we know that there is no common ratio between the y values, meaning that the table here does not represent an exponential function.
What do you call it when an elephant passes out? An elephant! You try.
Okay, doing the same thing. So is there a common difference between the x values here, from 0 to 1, from 1 to 2, and then from 2 to 3? Yeah, common difference between each of the consecutive x values. Now, is there a common ratio between the y values? So here, let's try. What's 9 divided by 6? That's going to be 1.5. What is 18 divided by 9? That's going to be 2. So technically, you could stop right here. This is not a common difference. Or you could just do the last one because, I don't know, you want to. 33 divided by 18, yeah, that's not the same. So because there is no common ratio between the y values, you could say that this table does not represent an exponential function. Here, we have a difference of our x values from 0 to 2 of 2. Now, from 2 to 4, that's the same. We're still adding 2. And then from 4 to 6, still adding 2. So there is a common difference between our given x values. Perfect. Now, what about our y values? Is there a common ratio? So 9 divided by 1, that's going to give you 9. 81 divided by 9, going to give you 9. And then 729 divided by 81, also going to give you 9. Therefore, there is a common ratio between consecutive y values. So, because there's constant difference between the x values and a constant ratio between the y values, you could say that the table represents an exponential function. Okay, example 2 says determine whether each rule represents an exponential function. Explain why or why not. So here we're given a function rule. Now, first and foremost, in order to determine is this a exponential function, the first thing you need to check is your exponent a variable. So here our exponent is x. It's a variable. Perfect. So that is the first thing you should always check. Next, is your a value not equal to 0? Yeah, it's 4, right? Perfect. And then is your b value greater than 0 and not equal to 1? Yeah, it's 5. Cool. Because those three things check out, you know that this function rule represents an exponential function. It's in the form y equals a times b to the x minus h plus k. Here, f of x is equal to negative 2 times x squared. So the first thing you need to check is your exponent a variable. Here, it's 2. No, that's not a variable, right? Your variable is the base. Therefore, this function rule does not represent an exponential function. Here, we have y equals 8 times x to the third plus 9. It looks like it's going to be in the form y equals a times b to the x minus h plus k, except for the fact that our first thing we always check is your exponent a variable? No, it's 3. Because your exponent is not a variable, this is not an exponential function. Lastly, we have y equals negative 9 times 6 to the x minus 1. Now, your first question, is your exponent a variable? Yeah, look at it. It's x minus 1. Okay, it's okay that there's a minus 1 here. That's just your h value. So here, yes, your exponent is a variable. It's x. Now, the question after that, is your a value not equal to 0? Nope, it's not 0. Perfect. And then is your b value greater than 0 and not equal to 1? Yeah, it's 6. So, because it's in the form y equals a times b to the x minus h plus k, where a is equal to negative 9, b is equal to 6, h is equal to 1, and then k is equal to 0 because there's nothing added or subtracted here. Just like up here, your h value was 0 because there's nothing added or subtracted to your exponent. You know that this rule represents an exponential function.
How do elephants keep cool? Air conditioning! You try.
Okay, so first we have our function rule here. Is this an exponential function? Well, does it have an exponent that's a variable? No, right? It's negative 4. So your variable is not your exponent. Therefore, it can't be in the form y equals a times b to the x minus h plus k. Therefore, this is not an exponential function. Here, is your variable an exponent? Yeah, our variable here is the exponent. Perfect. So we know it's in the form y equals a times b to the x minus h plus k. The question is a not equal to 0? Yep. Is b greater than 0 and not equal to 1? Yeah, it's 0.25. Okay, so we could say, because it's in this form, where our a value is negative 5, our b value is 0.25, our h value, there's nothing added or subtracted in our exponent, so that's 0, and then our k value is this number that's added at the end, negative 3. Therefore, this rule represents an exponential function. Down here, first thing we check, is our exponent a variable? No, there is no exponent here. Well, there is an exponent, but it's just 1. Therefore, this is not going to represent an exponential function. For part D, it looks like it's in the form y equals a times b to the x minus h plus k. Is our exponent a variable? Yeah, it's x plus 2 technically, but yeah, our variable is in the exponent. Therefore, it looks like it's going to be an exponential function. But let's check. Is our a value not equal to 0? Yep, that checks out. Is our b value greater than 0 and not equal to 1? Yeah, it's 1/2. So we could say, because it's in this form where a is equal to 11, b is 1/2, our h value is technically negative 2 because it's x minus h, so this would be negative 2, and then our k value is 0. This rule represents an exponential function. Example 3 says evaluate each function for the given value. So here, we're evaluating f of x is equal to 20 times 0.5 to the x power for x equals 3. Well, this is actually really easy. All you have to do, you're going to plug in 3 for x. So this is going to be f of 3 is equal to 20 times 0.5 to the third power. Now, please don't get confused like this is like 3 times f. We've done this a couple times. I just want to make sure you know. All this is saying is we are evaluating our function f at an x value of 3. So it's just saying if you were to plug in 3 for x, what does the function equal? Well, if I plug in 3 for x, I need to simplify this. What's 0.5 to the third power? That's 0.125. And then what's 0.125 times 20? That's going to be 2.5. So the function, when you plug in 3 for x, is equal to 0.25. That's what this is saying. Here, the function g of x is equal to 0.1 times 2 to the x power plus 3. And we're evaluating that at x is equal to 5. So we say g of 5 is equal to 0.1 times 2 to the 5th power plus 3. So what is the function g equal to when you plug in 5 for x? Well, let's find out. So order of operations, we take care of our exponents first. What's 2 to the 5th power? 2 to the 5th power is actually 32. Then we multiply or divide from left to right. So we multiply 0.1 times 32, you end up getting 3.2, and then we add or subtract from left to right. So what's 3.2 plus 3? That's going to be 6.2. So g of 5, the function g, when you plug in 5 for x, is equal to 6.2.
What's the difference between a mouse and an elephant? About a ton. You try.
Okay, we're doing the same thing here. So p of x is equal to 16 times 3 halves to the x power, and we're evaluating that at x is equal to 4. So we say p of 4 is equal to 16 times 3 halves to the 4th power. Now, we talked about this before. Anytime you have a fraction raised to an exponent, you need to raise the numerator to that exponent and the denominator to that exponent. So what is 3 to the 4th and 2 to the 4th? 3 to the 4th we know is 81. 2 to the 4th is 16. Now, what is 16 times 81? Well, technically, this is 16 over 1 times 81 over 16. So the 16s actually cancel each other out and just leave us with 81. So the function p, when we plug in 4 for x, is equal to 81. Here, for part B, g of x is equal to negative the quantity 1/3 to the x power plus 8. And we're evaluating that at x is equal to 2. So that means that g of 2 is equal to negative 1/3 to the 2nd power plus 8. So here, order of operations. What do we need to do first? Well, we need to square this fraction first, right? Exponents first. Then we multiply it by this negative 1 that's here. And then we can add the 8. So 1/3 squared. How do we do this? Well, you square the numerator and the denominator. So what's 1 squared over 3 squared? That's going to be 1/9. Then we can take that negative that was out front and multiply it to that, and you get negative 1/9. Lastly, we add the 8 to this negative 1/9, and we end up getting 7 8/9. You could also convert that to an improper fraction if you'd like. It's just pretty easy and simple to do this, though. Example 4 says evaluate each function over the domain -2, -1, 0, 1, 2, then determine if the function represents exponential growth or decay. So here we have our function, f of x is equal to 5 to the x power, and we're evaluating each function over this domain, which means we're going to fill out a t-table. So here's our t-table. We have an x, and we have an f of x, an x and a y, because f of x is the same as y. And we're evaluating it over this domain. Domain represents the x values. So we're going to take these guys and plug them in for our x values over here. Now all we have to do is get the y values that go with each of these x values. So let's start with -2. If I were to plug in -2 for x here, f of -2 equals 5 to the -2 power. Now what's 5 to the -2 power? I need to make this negative exponent positive, so it becomes 1 over 5 squared, which is 1 over 25. That's the y value that corresponds with this -2 as our x value. Let's try -1. If I were to find f of -1, I plug in -1 for my x. To make this negative exponent positive, I have to move it to the denominator, so it becomes 1 over 5 to the 1st power, which is just 1 over 5. So that is the y value that corresponds with an x value of -1. Now what about an x value of 0? So I take 0, plug it in for x in this function. F of 0 is going to be equal to 5 to the 0 power. Now what's anything to the 0 power? That's just 1. So I plug in 1 for my y value here. And then what y value corresponds with an x value of 1? So I plug in 1 for x. What's 5 to the 1st power? That's just 5. So 5 is the y value that corresponds with an x value of 1. What y value corresponds with an x value of 2? I take 2, plug it in the function for x. What's 5 squared? That's 25. So 25 is the y value that goes with an x value of 2. Now the question is, determine if this function represents exponential growth or decay. Well, it looks like as your x values are increasing, your y values are increasing exponentially, right? They're getting much bigger, much faster. Therefore, this would represent exponential growth. You could also know that by looking at your b value, because technically your b value is whatever is being raised to the variable, right? The exponent. Your b value is greater than 1. Since your b value is 5, you know that this has to be exponential growth. For part B, we're going to do the same thing. We have g of x is equal to 1/2 to the x power. Now, again, we're creating a t-table, and we're going to use these x values, plug them in for x, and see what y values we get. So, g of -2. So if I were to plug in -2 for the function for x, I have 1/2 to the -2nd power. Now what is this? Well, again, anytime you have a fraction raised to an exponent, you have to make sure that your numerator and denominator both get that exponent. So this is technically the same as 1 to the -2nd power over 2 to the -2nd power. Now to make a negative exponent positive, I move it to the opposite side of the fraction bar, and now I can simplify this. What's 2 squared? That's 4. What's 1 squared? That's 1. So 4 over 1 is just 4. So that is the y value that corresponds with an x value of 2 for this function. Next, we need to figure out what do we get when we plug in -1 for x. So what is g of -1? Well, this is going to be 1/2 to the -1st power. And again, anytime you have a fraction raised to an exponent, that exponent has to go to your numerator and your denominator. So it looks something like this. Now, to make a negative exponent positive, we move it to the opposite side of the fraction bar. So this becomes 2 to the 1st over 1 to the 1st. Now that's just 2 over 1, which is 2. So that's the y value that you get when you plug in -1 for x. What about when you plug in 0? What's g of 0? Well, 1/2 to the 0 power, anything to the 0 power, is just 1. So that's the y value that you get when you plug in 0 for x. What do you get when you plug in 1 for x to this function? Well, you plug in 1 here, so 1/2 to the 1st power is just going to be 1/2. And then that's your y value. Easy. What about 2? So we plug in 2 for x, 1/2 to the 2nd power. Again, anytime you have a fraction raised to an exponent, that exponent goes to your numerator and your denominator. So that's going to be 1 squared over 2 squared, which is 1 over 4. And that's the y value that goes with this given x value. Now the question is this exponential growth or decay? Well, as your x values increase, it looks like your y values are decreasing exponentially. So this would technically be exponential decay. Now, you know this because your a value is technically 1. Your b value is being raised to the x power, right? So you know your b value is actually this 1/2. Since your b is between 0 and 1, that's how you know this is exponential decay.
What's big and gray and hates Sleeping Beauty? Malevolent! You try.
So again, doing the same thing here. We want to evaluate the function over this given domain. So we're going to make a t-table. We're going to plug in these for our x values and see what y values we get when we plug these in for x. So what is h of -2? Well, if I plug in -2 for x, again, to make a negative exponent positive, we need to move this to the opposite side of the fraction bar. So this would be 1 over 0.25 squared. Right? It's positive 2 now down here. And what's 0.25 squared? That's 0.0625. Now the question is, what's 1 divided by 0.0625? That doesn't seem like it'd be a whole number, but it actually is. It's 16. So that is the y value that you get when you plug in -2 for x. What about -1? Plug in -1 for x. What is 0.25 to the -1st power? That's the same thing as 1 over 0.25 to the positive 1st power, which is 1 over 0.25. Now what's 1 divided by 0.25? That's actually 4. So that's the y value that corresponds with -1 when you plug that in for x here. What about when you plug in 0 for x? 0.25 to the 0 power? Well, anything to the 0 power is equal to 1. So that's why this is going to be 1. Now, what's the y value you get when you plug in 1 for x? Well, h of 1 is equal to 0.25 to the 1st power, which is just 0.25. So that's the y value you get when you plug in 1 for x. What about when you plug in 2 for x? Well, h of 2 is going to be equal to 0.25 to the 2nd power. Now, what's 0.25 squared? That's going to be 0.0625. So that's the y value you get when you plug in 2 for x. Now, the question is this exponential growth or decay? Well, you can see as your x values increase, your y values are decreasing exponentially. Therefore, this is going to be exponential decay. And you know that because here your b value, the number being raised to the x power, is between 0 and 1. Because of that, you're going to get exponential decay. Here we have p of x is equal to 0.4 times 2 to the x. Here we actually have an a value that's not equal to 1 now. It's 0.4, and then your b value is 2. So we have a t-table, and we want to plug these in for our x values, and we're going to plug those in for x to see what y values we get. So p of -2. If I were to plug in -2 for my x value, I get 2 to the -2nd. Remember, I have to deal with my exponents before I multiply it because of order of operations. So what's 2 to the negative 2? Well, to make a negative exponent positive, I make that 1 over 2 squared, which is 1 over 4. Now, what's 0.4 times 1 over 4? That's going to be 0.1. So that is the y value you get when you plug in negative 2 for x here. That's p of negative 2. What's p of negative 1? So when I plug in negative 1 for x, I again need to deal with my exponent first. So this becomes 1 over 2 to the first, which is just 1 over 2, times 0.4, which becomes 0.2. So that's the y value that corresponds with an x value of negative 1. What's the y value that corresponds to the x value of 0? So p of 0, I plug in 0 here. What's 2 to the 0 power? That's going to be 1, because anything to the 0 power is 1, times 0.4. That's 0.4. So that goes here. And then 1, I'm going to plug in 1. So what's p of 1? 0.4 times 2 to the first is going to be 0.8, because this is just 2. 2 to the first is 2, and then 2 times 0.4 is 0.8. So that's the y value that corresponds here. And then lastly, we're going to plug in 2 for x. 2 squared is going to give me 4. And then what's 4 times 0.4? That's going to be 1.6. So that's the y value that corresponds here. Now the question, is this exponential growth or decay? Even though it's moving very slowly, right, as your x increases, your y values are increasing, it looks like slowly, but they're actually increasing exponentially, which means this is exponential growth. And you know this because your b value here is greater than 1. Now our word problem says an investment of $5,000 doubles in value every decade. The function f of x is equal to 5,000 times 2 to the x, where x is the number of decades, models the growth of the value of the investment. How much is the investment worth after 30 years? So, first thing we do, word problem, not scared. Step 2, define our variables. What is this question asking? It's asking how much is the investment worth after 30 years. So what we're going to do is we're going to say, all right, f of x is going to be equal to the total worth of our investment. You could have made this some other variable, but if you look ahead, we already are given an equation, so maybe we use that as our variable here. So f of x is equal to our total worth of our investment, which means x is going to be the number of decades. Cool. So we have our two variables. Now, what is our equation? Awesome. It already gives us the equation. That's super easy. So all we have to do is evaluate. It says how much is the investment worth after 30 years? Well, remember, x is the number of decades, and 30 years is 3 decades. So we're going to plug in 3 for x. So we're going to evaluate f of 3. So when we plug in 3 for x, again, order of operations, we have to do the exponent first. What's 2 to the third power? That's 8. And then we can multiply. What's 8 times 5,000? That's 40,000, which means that the investment is worth $40,000 after 30 years. Please answer in the form of a sentence.